These are chi-square testing notes 1, goodness of fit test. Please read the information that is bulleted at the top of your worksheet. This will give you some information regarding this type of test. I want to get right into the notes for this unit because there's a lot of things that we need to cover today. This test is called a goodness of fit test, and it follows the same type of format that we use for significance tests that we learned in our last unit. First of all, the hypotheses for this type of test can appear in a couple different formats. The null hypothesis, because we're going to be working with multiple proportions, may appear to look something like this. There might be one proportion, we'll call it P1, which equals something. There may be a second proportion which equals something. Could be more than two proportions, could be 3 or 4, and we'd list them out whatever they happen to be here. For the alternative hypothesis, we would say something to the nature of at least one of these proportions is incorrect. Or sometimes based on the question that's stated, the null hypothesis might say something is proportional to something else, and the alternative hypothesis would be something is not proportional to something else. Or sometimes the problem will be worded even differently, in which case just use wording from the problem. The procedure that we're using is a chi-square goodness of fit test. You don't have to write it out using the letter CHI. You can actually say chi-square goodness of fit test. Now onto the condition step. For our first condition, again, just like we've had for every test we've used so far, random sample from the population can be the first condition. What you can also use are independent observations. So if it appears that we have independence going on, you can name that as your first condition. What you want to do in step 2 is you want to show a table of expected values. This will make more sense once we get into an actual example. Now the table is not actually a condition, it's that the table has these two characteristics. All of the values inside this table, all of the counts need to be at least 1. In addition, only 20% or less of the counts are allowed to be smaller than 3. If these conditions are met, we're allowed to continue with this type of test. In our third step, we carry out the procedure. Chi-square is our test statistic, and to calculate chi-square, what we do is we take a summation of observed values, which are typically given to us in the problem, minus expected values that we'll generate, and I will explain to you in a few minutes how you do that. We're going to square this difference, and we're going to divide it by the expected values. Just like in our other tests, we can identify degrees of freedom like we do in our t-interval problems or t-test problems. Degrees of freedom in a chi-square test are equal to n minus 1, where n is the number of categories, not the number of items in the sample, but the number of categories that you're working with. Again, we'll explain what this means a little bit more later on. You also want to identify your p-value here so that when we interpret our results, we use the same script that we used in past work. Let's move on to the back side of your worksheet. You're going to notice a problem from the 2008 AP exam. What I'd like you to do is pause the video, read through this example, and we'll start off with answering this question in just a moment. To answer this question, Part A says, the researchers who are conducting the study expect the number of moose observed in a habitat type to be proportional to the amount of acreage of that type of habitat. Are the data consistent with this expectation? So I think you have a couple of options for writing your hypotheses here. The first type I'm going to look at is using our symbols. So I'm going to say H sub O for our null hypothesis. And we're going to talk about what these proportions should be. I would expect that P1 should be 0.340. P2 should be 0.101. P3 should be 0.104. And P4 should equal 0.455. P in this case being the number of moose are proportional to the amount of acreage, so this proportion of acreage should equal the proportion of moose that exist in each of these habitat types. For the alternative hypotheses, at least one of these proportions is incorrect. And you do want to state what these p-values represent here. So to generalize it, I'm going to say where p sub k is the proportion of moose in habitat k. I think you could also word the hypotheses in terms of the question, so you could say for the null hypotheses, the number of moose observed in habitat is proportional to the amount of acreage of that type of habitat. No change. which means that we're basically plagiarizing this statement right here. The alternative hypothesis is going to be the negation of this statement, which would be the number of moose in a habitat type is not proportional to the amount of acreage of that type. You do not have to write down both of these sets of hypotheses as long as you have one of these null and alternative hypotheses, whether it be this first set or this second set. That's sufficient for this problem. It's your choice. Both ways are correct. In the second step of this problem, we check conditions. You'll notice that this glorious statement, assume the conditions for inference are met. Hooray, we are going to write that down. However, we are still going to write down the chart of expected values even though we are going to assume the conditions for inference are met. The expected values table is going to be attached to this observed values table that's already been created. So I'm going to add another column to this chart here. And this column is going to contain the number of moose expected. Now, how do you figure out how many moose we should expect? Well, we know how many we've observed. That's 117, and that's going to be the total number for the number of moose expected as well. We also have a proportion of total acreage. Now, if the proportion of moose observed is the same as the proportion of total acreage, what we should see is 34% of our moose is what we would expect. And 10% of our moose should be in habitat 2, and 10.4% should be in habitat 3, and 45.5% should be in habitat 4. So what we're going to do is we're going to take these proportions that are listed in this column, and we're going to multiply them times this total, which is at the bottom of this column, and these products we're going to write inside here. For example, for this first item, we're going to take 0.340, and we're going to multiply it times 0.1, and we're going to multiply it times 117. This gives you 39.78 when you calculate it on your calculator. What I'd like you to do is pause the video, multiply each of these proportions by 117, and write down those values in this expected column. So our expected number of moose that we have should be 39.78 for habitat 1, 11.817 for habitat 2, 12.168 for habitat 3, and 52.235 for habitat 4. If you were to actually add all four of these values together, you should get 117, or approximately 117. Now let's move on to step 3, where we actually calculate the chi-square statistic. To calculate chi-square, what we do is we take a sum, and we're going to take the sum of each of the observed values in our table minus each of the expected values in the table. We're going to square that difference and divide by the expected value from that particular value. In this problem, what we're going to do, if I refer back to the table, is for the first habitat type, the observed number of moose was 25. We're going to take this number minus the expected number of moose for that habitat, 39.78. We're going to square that and then divide again by the 39.78. We'll do that for each of the four habitat types, and then we're going to sum those four items together. It should look like this. So here are the sum of the four different categories that we're working with in our table. When you type this in your calculator, you're just going to put parentheses where you see them, so you'll have 4 sets of parentheses. It's a lot of things to type out, I admit that. But you don't have to add any more parentheses than what you see here. If you actually crunch this out, what you're going to end up with is approximately 43.69. Now for this type of test, you're also going to identify the degrees of freedom. The degrees of freedom is not the sample size minus 1, so it's not 117 minus 1. It's the number of categories or habitat types in this problem. So for n minus 1, we have 4 habitat types. It's going to be 4 minus 1 equals 3. It's not going to be 117 minus 1, which equals 116. It's just going to be 3. For the p-value, I'm going to bring in my calculator. I first want to show you how I got that result of 43.69 that we had written down earlier for our chi-square value. So you can see the values that I typed in my calculator. To calculate what the p-value is equal to, we're going to go to the second var. So we're going to go to the distributions option on your calculator. And under this category where we've seen normal CDF before and binom PDF, you're going to see, hey, there's a Greek letter chi, and there's a chi-square PDF and CDF function as well. We're going to select the chi-square CDF option. What we're going to type in is this value. Now you can actually type in the rounded value, which we wrote on the paper, 43.69, or you can use your answer. I'm just going to go second answer. or you could type in 43.69. Afterwards, we're going to type in basically the number infinity. You don't have to go that far, though. If you just want to use 99 or 999, that's okay as well. Comma, the degrees of freedom for the problem, which is 3. What this generates is your p-value, which is 1.76 times 10 to the negative 9th power. I'm going to write that down here. What this actually means is that on a chi-square curve is actually a right-skewed graph. And what we're shading in here is wherever this 43.69 value is, which would be really far down our curve, everything from here to the right. So we're shading in from 43.69 up to essentially infinity. And really 43.69 is really far down the curve. So we're talking about a very small region of your graph that's being shaded in here. Then you should know how the conclusion works. Since our p-value is less than 0.05 or less than any significance level that might be established, we're going to reject the null hypothesis. There is significant evidence that, and now we write the alternative hypothesis in words. Usually what I'm going to say is I'm going to avoid at least one of these proportions are incorrect. I kind of like the statement that we used in the second alternative, which is the number of moose in a habitat type is not proportional to the amount of acreage of that type. A quick note for this type of test, you do not have to show the graph. It is sufficient just to show the chi-square value, the degrees of freedom, and the p-value. If this seems a little tricky, if you're like, wow, some of these steps are goofy, remember how it was when we started confidence intervals or even significance tests. It was kind of difficult at first. After we did several problems, it gets a lot easier. So the same thing is going to be true with this unit as well. Tonight for your assignment, what you're going to be working on is problem 13.2 and 13.4. You're just going to be doing the third step. Now you may need to actually finish up a table of expected values because you're going to need expected values to calculate chi-square. But for tonight, you can disregard the hypotheses, everything other than step 3, and you're going to be doing 13.2 and 13.4, this third step.